So what did we look at last class? So we looked at dummies, right? I think Ankesh, you had a question about whether this dummy would be minimum length or would it be longer length or something. So why would you want to make it minimum length? Just to save area? Okay. So normally you want, okay, so the gate shadowing effect is one effect which we talked about. There are actually a couple of other effects which also go on. Okay, so typically you want that to be identical to your main transistor. Okay, we'll actually look at, I think we'll look at one of those effects today, where it doesn't directly depend on the length, but it actually depends on the region of active around your around the transistors. Okay, we'll look at one of those today. Okay. Okay, so we are looking at dummy transistors in the layout. So one of the other things last time we were looking at, let's say if you're using multiple transistors, you just add multiple units, you just add one extra dummy at the end for the array. But you can also do the same thing. So let's say you just have a single transistor, but let's say you're interdigitating them, single set of transistors. Okay, so what you can do is you can make you can add two more fingers at the end. Okay, that's all. So if you have, let's say, 20 fingers, just make it 22 and make the last two as dummies. You can just connect all the inputs and outputs to ground. So drain, source, gate, everything can be connected to ground. Okay. So you can add dummy finger. Okay. So the other thing you need to worry about is something called, okay, so these are what is very common in these new processes is something called shallow trench isolation or STI. Some of you might have heard about it, right? So this is typically the most common type of isolation between different transistors. So basically if you have, let's say this is your transistor. Okay, you basically have some kind of trench on the sides. Okay, what happens is, so because of, let's say if your temperature changes, these trenches cause some amount of stress, okay, to the desired transistor. Okay, and the closer they are, the more stress they exert. So what happens is that stress can actually change your all kinds of parameters. It can change your VT, it can change mobility. Okay, so at the end of the day, what you're interested in is, like, let's say transfer parameters like GM and so on. It will definitely change all of those. So what ends up happening is you are designing for a particular GM, but the GM will be off by, it can be as in some of these deep submicron processes, it can be off by as much as like 15-20%. Okay, which is a lot, obviously. Okay, so the other thing is you can also if you add dummies on the sides, it helps isolate your main transistor from your trench, okay, from the effects of the trench. So obviously that will increase this distance. Okay, so that's another reason why you want to have some extra keep out region. Okay, there are a bunch of things like this. Okay, so for example, well overlap over your active. Okay, so there are a bunch of things. So for example, let's say if you had a PMOS transistor and you had a well like this, you want this distance also to be larger than a certain amount. So you have requirements for that. Okay, the more overlap there is, the less effect you will have. Okay, so there are, you just have to know a bunch of these things. Coming back to your shallow trench isolation. So for example, you can build a simple current mirror. Okay, and depending on this distance, okay, you can try to plot, let's say you can try to plot your mirror ratio versus your separation from the trench, the distance from the trench. So it will probably look something like this. Okay, so if this is that distance d and this is your error percentage, so if this thing is very low, it'll look something like this. Okay, so if you have very little distance, you'd actually find a lot of error. Okay, but then after some time it actually starts to go down, and obviously beyond a certain point you really don't care. You know, there will be other mismatch effects which come into play, so you don't really worry about it. So there will be some optimum distance. So let's say it will be a few microns, maybe 3-4 microns. Okay, so that is another reason why you want to have some extra distance and add the dummies, because you really don't care about the dummies. So other things in the matching environment, metal lines, for example. So we talked about having equal same environment as far as the transistors are concerned. So you add the dummies. How about metal lines? So let's say you have two transistors, but let's say you're only contacting on one of them. Okay, and but you still want matching. Okay, so then you still add the metal line, but no contacts. So that at least, for example, there will be overlap parasitic capacitance from the metal line onto this. Okay, so you have to worry about matching capacitances in an RF sense. Or you could, for example, have a supply line, let's say VDD, running just all the way here. So what you'll want to do is you'll probably want to extend it. Okay, very small things like this can make a big difference. Okay, so if you want to match two things, try to make as many things as possible identical between those two. Okay, I think the next one is, oops. As far as routings go, try not to make 90-degree turns. Okay, so if you don't do this, okay, if you want to do the same thing, try to do something like this. Bad. Okay, try to do something like this for all turns. Obviously there will be some cases where this will be counterproductive if the turns are very narrow. In those cases you may not be able to do it. Okay, because to do this 45-degree turn you need some length. So only lines of a minimum length can be made 45 degrees. But if you have that distance, go ahead and do it. Because what happens is, typically when you are looking at high frequency currents, you tend to have current crowding. I think we looked at this during when we saw the inductors, right? You'll end up having current crowdings right at the turns. Okay, and so your density will increase. There are a lot of effects. So you'll have there is something called electromigration, where if your current density increases in a particular point, your metal starts to erode. Okay, so you might have issues like that. So 45-degree turns are much better. Obviously, I mean, what doesn't need to be said is maintain symmetry for differential routings. Okay, so if you have two differential lines, try to maintain symmetry as far as the lengths of the line. Okay, the surroundings of the line. So for example, let's say if you have two things like this, so let's say the layout of each block is like this. Okay, so let's say it comes out like this. You probably want to do something like this. So what might happen is you can't. So okay, so the inverters themselves may be quite wide, whereas the routings themselves need not be so wide. So you probably have to do something like this. Don't bring them in. For example, don't bring in the line somewhere up here. Okay, and then try to split them, one like this and one like this. Don't do that, obviously. And similarly at the output. Okay, and the other thing to remember, so let's say these lines are routing out all the way. So let's say you have some routing here, try to replicate the routing here. These are all very basic stuff. Okay, so you're just trying to maintain the same environment, that's all. Okay, so we looked at, let's quickly look at, for example, how do you match between resistors, capacitors and so on. What are some good practices and how do you lay out certain things? Okay, so for example, first of all, I think for resistors, We never covered what kind of resistors, options you have. We looked at inductors, capacitors, varactors, and so on. We never looked at resistors. So let's quickly cover that before we go on to the layout of the passives. Okay. So you have 5 or 6 different kinds of resistors. You'll have many of them are based on silicon itself. So you have N type, you have P type, you have different kinds. There is something called silicided resistor. Silicided is basically you have a polysilicon piece, and then you add some metal deposition over that to reduce the resistance. Okay, so the metal forms a silicide compound with the silicon. Okay, and that reduces the resistance. So let's look at the different kinds. So if you have polysilicon resistors, typically whether silicided or non-silicided, they'll typically have very small values. Obviously the lowest values will be your metal routings themselves. They'll give you like up to probably a few ohms. These can probably give you a few tens of ohms. Okay. These will have a relatively low cap to substrate compared to the other kinds. Okay, not obviously compared to the metal. If you make a resistor, small value resistor with the topmost metal, that will have the lowest cap, but these will typically have lower cap to substrate. And in some processes they can have smaller mismatches. Okay. You can have them, you can use your P plus and N plus silicon diffusion to create resistors. So those would be low to medium resistances. Okay. So this will be typically, typically 3 to 5 ohms per square. So all of these resistors, all the resistors in the process will be given as you'll be given the sheet resistance. Okay, so you'll be given so many resistances per square. You make it wider, the resistance basically drops. Okay, and remember for all of these resistances, the wider, at least for most of them, the wider you make the resistor, the better the matching would be, because the change in the resistance for a given typically it's geometric variation which you are worried about. Okay, so if you make it wider, you will get better matching. Okay, so if you want to match 2 resistors, make them at least maybe 1.5 to 2 microns wide. Okay. The other thing is the diffusion resistor is going to be very sensitive to process and temperature. Okay, because obviously you're using the diffusion, so it depends on the doping levels, so therefore it's going to depend on the process. Obviously you're depending on the semiconductor property of the material, so it is going to depend on temperature, okay, including mobility and so on. Okay, then you can use your N well to create your resistor. N wells are typically high resistivity, higher than diffusion, so you can make high value resistors. Okay, and obviously this is also going to be process temperature sensitive. And the other thing to remember about N well resistors, obviously because now they are right next to your substrate, they are going to have a lot of cap, okay, lot of parasitic capacitance to your substrate. So in other words, don't use it in the signal path as much as possible. Okay, that's what it means when you have a parasitic cap in the RF signal path. For example, let's say you want to make a common source amplifier with a resistive load which has maybe 1 or 2 kilo ohms. You can get 1 or 2 kilo ohms with a very thin piece and very small piece of N well resistor, but you probably don't want to do that. Okay, you probably want to use a diffusion resistor. The other thing about the N well is the closer you go, it is obviously more sensitive to picking up things from the substrate. Okay, you definitely don't want to use those kind of things in your sensitive path. Obviously, there may be cases where you don't have a choice. Okay, for example, if you want, let's say, a 100 kilo ohm bias resistor, you may not have a choice, because if you use a diffusion, it may just become too big. Okay, so there you may end up having to use this. Obviously, we looked at this during the VCO. MOS resistor, if you want, really mega ohms kind of, resistance, you can use this. You can use a MOS resistor with a very, small, very small WRL. Okay. Okay. So, and the other thing to remember is flicker noise. Remember that ideally your resistors are supposed to have only thermal noise. Okay, but many of these resistors, well, not many of them, some of them could potentially show flicker noise. Okay, because flicker noise is inherently happens at interfaces between different materials, and when you rely on silicon based resistors, you naturally expect it won't be as high as MOSFETs or even bipolars, but there are some special cases where you could see flicker noise. Okay. Okay. How do you lay them out? So let's say you want to match two sets of resistors. Okay. So taking a very basic case. Okay. So obviously the gain of this amplifier depends on R2 over R1. So you want to have, so even though in the process the R values change by quite a lot over temperature and process up to plus or minus 20%, your ratio of the two resistors still manage to be, you can get good matching between them. Okay. So if you want, let's say R2 or R1 of let's say 4 or something like that. Okay. So let's take the case of 1. So if you want R2 or R1 equals 1. So obviously you want to lay them out in the same orientation, that is obvious. Okay, so that is for sure. Now if let's say if you have okay, if you have let's say 1:4 or something like that, you might want to or let's say 1:8 or something like that, you might want to lay them out make it much smaller. So let's say this is R2 and you could lay out something like this, R1 right at the center. Okay, you could do something like this. So main idea is to try to get a regularized array. You can add dummies around the other one if you want. How about capacitors? Again same thing, same orientation is a given. Okay, but there are other things. For example, so your cap is typically proportional to the area, right? So it's W times L. So suppose I have two options. So let's say this is W, this is L, this is W, this is L. Which one would you choose and why? Does it matter? Let's take the case of a metal oxide metal cap or a metal insulator metal cap, like a passive linear cap. Okay, does it matter which one you choose? So as far as the cap goes or as far as the parasitic go, it probably doesn't change too much. However, the first question I would ask is, where are you contacting them? Okay, are they contacting them from this side, the two caps? So let's assume that's the direction. So these are the two sides. Okay, so in one case you would contact them like this, in the other case you would contact it like this. Which is better? The second one is better, obviously, because you have a much wider connection, so your series resistance is much lower. Okay, so typically if you have capacitances, large value capacitances where you worry about the series resistance, definitely do this. Okay, what you can do is you can kill a perfectly good design by doing something very bad with the capacitors. For example, you want to have, I assume you guys all know about this. So let's just take some inductance in the supply, okay, and let's say your input is a clock. What is your output going to look like if you have some inductance in the supply? So first of all, this inverter is going to draw switching current, right? Every time it switches, it's going to try to draw some pulse of current. What happens? The inductor doesn't like changes in pulse of current. You're going to get LDI by dt drops. I assume you have seen this before in other courses, right? So what happens is, if you look at the voltage here, you're going to see actually much worse than this. If you just take, so you're probably going to see like this. Okay, it can go drop very low depending on the current you are drawing. Okay, it won't be VDD anymore. Like for the course, for the project, we're just assuming ideal VDDs. But in the real case, remember that from the circuit, you're routing a long way to the pad. You have a bond wire which goes off chip. You're going to route on the PCB and go somewhere else. Okay, so the best way to combat this is to add some cap. Okay, this is called the supply decoupling cap, right? So basically, the pulses of current will be drawn from the cap instead of through the inductor, because the capacitor acts as a huge reservoir of charge. So anytime it tries to draw pulse of current, the capacitor supplies it. Capacitor doesn't allow its voltage to change suddenly, so it stabilizes out this voltage. So you'll get something like this, and of course you will get some pulses, but depending on the size of the capacitor, it will become very small. Okay, now you're basically relying on the fact that the capacitance is low impedance for that pulse of current, right? If you have some series resistance with that, you can be pretty sure that you're going to kill your decoupling. Okay, and if you do something like this, a layout like this, it's a perfectly good way of killing your decoupling. Okay, similarly, you can show the same thing for your MOS cap. So let's say this is your gate. Okay, so you definitely want to make a good connection here. You definitely want this to be wide in some sense. Okay, don't make a very, you can get the same amount of cap if you do something like this. Okay, but obviously this will have a very large gate resistance. Okay, you probably don't want to do that. And again, for all of these caps, try to, because you're trying to get a lot of cap, let's say if you take a decoupling cap, you're trying, more cap is usually always better. So you don't care about parasitic caps. So don't mind, stacking up different metal layers on top of this. Okay, so don't worry about stacking metal layers on top of decoupling cap. Extra cap only helps you, right? You want to minimize the resistance, so try to stack as many metal layers as possible. Okay, what else? The other things I think, transistors. We already looked at this, splitting transistors into fingers and so on. But the one thing to remember is splitting into fingers can also be useful. Let's say even the capacitor, right? Instead of having one large capacitor or one large transistor, splitting into more devices can help in other ways. So one thing is if you have the signal transistor, but let's take the case of the bias. Bias transistors are typically much larger than the signal transistor. It helps you to actually do your floor planning. For example, this may be your signal, okay, but the extra space you have may only be here. Why? Maybe your signal input is coming here, output is going here. Okay, you could perfectly well have a case like this. So if you have something like this, where would you place the bias? So you can split the bias transistors. Okay, very nicely. Bias transistors, as long as they are laid out in an array here internally, you can have some decent matching. Okay, you don't want to spread it out too far, but you can try to change it, work around it. Or for example, you may not, your bias you may split like this. This may be cap. Cap, you can spread it around, and that's usually perfectly fine. Okay, you have something called antenna effects. Basic idea is, so let's say you have a very large sheet of metal connected to the gate of a transistor. Okay, so typically what can happen is during your etching, and your processing procedure, this thing can build up charge, because remember you are laying out layer one by one. So this typically after this metal layer is done, it is a standalone metal layer, it's not connected to anything. Okay, so this can pick up a lot of charge and then break down your gate. Okay, discharge through the gate and break it. Okay, break it down. So if you want to, typically if you want to prevent this, one common way is to add a reverse bias diode, a very small. So you have rules for that. So for a given amount of area, you need to have a certain amount of diode, reverse bias diode connected to your long lines. Or what you could do is, you could split this up such that it goes up to one metal layer and then comes back down. You can add vias to break the connections to your gate. You can do techniques like that. Density. Okay, how about so one of the requirements from the process is, if you have, so for the integrity of the process, the device engineers require you to have a minimum density or minimum percentage of area covered with certain layers, and typically most layers will have that. Okay, and for some layers it will be small, other layers this density will be large. Typically for metal, you need to have 80% of your device, of your chip area covered with metal on each metal layer. This is very typical. Okay, rather actually, yes, that's right. So it could be 80%. Let's say 80%. Okay. So you could have requirements like this. So what you have to do is, obviously your circuit routings and everything are going to contribute maybe 10% or 15%, probably not much more. So if you want to make this up, you'll typically have to do what is called fill for your transistors. So you'll have to put in what is called dummy metal. They'll be just floating pieces of metal. So your block may be here, and on top of that, so they'll put in dummy pieces of metal on all metal layers. Okay, it will just be an array, and typically you won't even be able to see your circuit once it's filled. Okay, and now you obviously, for sensitive circuits, you want to prevent this. So you will have to make sure. So typically for RF circuits, for the signal portion of the circuits, you definitely want to do what is called custom fill. So there are auto programs. Obviously it will find out what metal layer is available already there, and it won't fill on that metal layer, but it will fill on other metal layers. Okay, but you don't want to do that. Okay, so normally what you would do is, so you'd have a signal portion and you'd have a bias portion, let's say, and you can fill here. Okay, okay, and you normally want to do what is called custom fill, which is filling by hand. So you go in and keep putting, little by little, filling them in. That's, you definitely have to do that. And again, so let's say, so you have differential lines. Again, you have to be very careful about the fill. Okay, make sure your fill is symmetric. Something like this. Make sure it's symmetric. Okay, for example, don't fill on one side, not fill on the other side. Don't fill one side farther away than the other side. So those are all things you have to take care of. Okay. And typically what you'll have to do is, around inductors, you can leave out fill. Okay, normally around the inductors, the foundry will give you some waiver, because obviously the inductor is going to be huge. It may be 200 microns by 200 microns, and that means that your that area is definitely going to have low density for lower metals. Okay, and you can't do anything about that. Okay, and usually the foundry will tell you, okay, they'll give you something called a waiver. They'll review the layout and they'll give you a waiver. Okay. What else? You can fill. Obviously, we looked at filling on the bias circuits. The other thing to know for transistors, don't stack up too many metal lines here. on the drain source, okay, because you'll have extra capacitance to the gates, okay. Fill up just enough so that you meet current density requirements. So let's say you have to route a long way. So let's say from your VCO to your mixer, or from your VCO to divider to your mixer. Okay, so you can have very long lines. So first of all, so let's say it's like this, and let's say this is your divider. Let's say this is 1 millimeter, something like 1 millimeter. Okay. First of all, how will you design these lines? Would you make them wide? Would you make them thin? What metal layer would you use for them? You would make them very wide. Why? Sorry? Oh, the resistance of the lines. Okay, so you want to make them wide because of the resistance. Okay, but what happens if you make it wide? Obviously, you'll have some extra capacitance, and you have to be careful, because if you add too much capacitance, then you'll be burning a lot of power trying to drive it. Okay, so at the end of the day, there will be, what you will see is, if you look around at these RC values, there will be a certain optimum resistance and capacitance, okay, and an optimum power which you can. So you'll make them. Oh, obviously L opt is not there. Okay, so obviously there will be an optimum width. Okay, now the next question is, if they're going from the VCO to the divider, they're going to be very sensitive lines. Do you want to add a shield for them? So let us say you add a shield on both sides. Okay, what happens? So now you have some extra capacitance to the shield apart from the substrate. So you have the capacitance of the substrate already, you are basically adding extra capacitance. Okay, so now you need to space them out wider. Okay, now again, if you space them out wider, then you're using up more area. First of all, the second thing is, if there is something coming in from the substrate, okay, this thing might pick it up. Okay, but yeah, so you can't do, you can only do so much area. Okay, okay, there will be metal lines. Okay, so let's say this is on M3, so these will also be on M3. Okay, you can actually make a multi-layer shield also. For example, if this is on M3, you can add shield on top on M2, on M4, and shield on bottom on M2 also. So you can basically make it a square thing. But remember, this distance you can actually control. The vertical distance between the metals you cannot control. So typically you don't prefer to add a shield on the bottom. Okay, you would, if you are going to add, you typically add it on the sides. Okay. Yes, so which is why you're not going to add on top of it, you're going to add to the side. On M4 or M5 on top of this, you typically don't want to cross. You don't want to cross these two lines, sensitive lines at all. Now there may be cases where you are forced to cross, in which case you make those cross lines extremely small, so that extremely thin, okay, and short. Obviously you don't run lengthwise, you run perpendicular. That is one thing you can do. Second thing, you can, for example, use it on as far away a metal layer as possible. Okay, so if this is on M3, you either want to do it on M6 or on M1. Okay, depending on the signal. So you may not be able to do it on immediately adjacent metal layer. We'll add extra cap. Next we'll look at substrate contacts. So let's just take the case of a transistor. So normally, okay, so let's take the case of an inverter, okay, so that maybe that's the easiest. Let's take an inverter with 2 fingers. So normally, your substrate and ground would, let's say this is your VDD and ground, and you would put your substrate contacts right below your VDD and ground lines, okay. Look like this. But if your circuit is sensitive, you may also want to put in contacts here on the sides. Okay, because you want to give a really good substrate. Remember that a lot of transistor parameters depends on the substrate. Okay, things like threshold voltage and those things. If there is any substrate current, right, and there will always be some RF current being sent into the substrate. Okay, what you will see is if the substrate has some, let's say, some series resistance, that will build up a voltage. Okay, and if your substrate voltage is wiggling, then what happens is your transistor threshold voltage is changing over time, for example. Okay, so you want to prevent that, so you want to give a very good substrate contact. And typically, so there will be specialized RF transistors which are very well modeled. Okay, so these, if you look at the basic transistor model, they basically just model all the way up to M1, probably just enough to give contacts and connect it out. Okay, any metal lines added up are not modeled. If you add substrate contacts, they are not modeled. However, every process, especially an analog or RF process, will have an RF transistor, which would typically have, you'd have the transistor and you would have actually a substrate ring around it. Okay, and this transistor as a unit will be modeled. Okay, including the impedances, the resistances of substrate and so on, everything will be modeled. So typically if you use an RF transistor, what you see is what you get, as in if you design for a particular thing, it will be modeled based on because your layout is perfectly fixed. Usually you will measure what you wanted to measure, okay, from the transistor itself. Okay, so that's as far as your subcontacts go. So what does the substrate contact do? So if you have, let's say, a switching transistor, so let's say you give it an inverter and then you give it a clock signal, the substrate will always have some impedance, some inductance or whatever, right, some impedance. So definitely your substrate will be wiggling. So what effectively is happening is your transistor, your noisy transistor is injecting something into the substrate. Okay, if other transistors share the same substrate, they can actually get through that substrate they'll pick up this noise. Okay, and that's one of the reasons why you're trying to give this substrate contact, because your substrate at the end is going to be connected to a central ground somewhere else, far away. Okay, so you want to give it a very short local ground, because what will happen is this will be running on metal. Okay, so this will be, the substrate contacts will be routed on metal. And then they'll be connected to ground on metal. So you'll be giving a very good contact. That's the idea. Okay. Now, so let's say you have built your circuit as a block. Okay. Around your overall circuit, it's actually not uncommon to put what is called a guard ring. Okay. So the main idea is, so let us say there is a noisy block right next to this block, okay, and which is injecting something into the substrate. So you want to pick it up before it reaches your sensitive circuit. So in that case, you would put something like a guard ring. Okay, so if you have a noisy thing which is this thing, so it will get pulled up through the metal and go straight to ground, which is through the low impedance path. Okay, so typically a substrate ring will prevent your circuit from injecting noise into the substrate. A guard ring would protect your overall block from picking up things. Okay, and now obviously, okay, so let's say now you have a guard ring and you have a substrate ring inside. Okay, so remember, because these two have totally different functions, do not connect them at the end to the same ground. Okay, so don't, let's say this is your ground pad, use a separate ground pad for the substrate ring. If you end up connecting these two, it's the same thing as almost the same thing as not having the guard ring. Okay, because at the end of the day, it is going to go out like this through the low impedance path and come back to the substrate directly. You understand what I'm saying, right?
Then we will connect those two contacts.
Sorry?
We will connect those two.
Okay, so these two will be pads. So you'll have a bond ring. So the idea is to increase the impedance between those two paths, so that at any time the noise current has a choice between which paths to flow. It will flow through the low impedance path. So obviously at some point of time it's going to be connected up, but you keep increasing the impedances along these paths until when the noise wants to split, right? So let us say it's coming here, at this point the noise wants to split, you're going to have a very good connection to ground on the PCB, let's say. So it is going to prefer to go there instead of coming back through this. That is the idea. Try to increase the impedances on the two paths.
That means apart from ground we should have two more
substrate, one for garden.
Apart from what?
Apart from normal ground.
Okay. Apart from that will be your best choice. Okay, that will be your best choice. There are obviously cases where you may not have so many pads. In which case you would have to decide. So depending on whether the circuit is noisy or whether it's you're interested in protecting it, you'll have to decide to group the grounds together. That is a totally different topic by itself. That is something you definitely will have to make a choice there. If it is a very sensitive circuit, most people would prefer to connect its own substrate to its own ground, okay, rather than connect it to the guard ring, especially if there's a noisy circuit. So it depends on a number of things. It depends on the surrounding environment. It depends on this circuit itself. So I'll give you an example. So if you just take a switching inverter, right, it is going to be pumping something into the substrate. If you connect it to its own ground, you want to keep its ground clean, okay, for the inverter to switch well. If you connect it to its own ground, you may end up spoiling, your own inverter switching characteristic. So there you may have to be careful. Okay, you may choose to do the substrate, ground and guard ring connection differently from, let's say, if you had a VCO or if you had an LNA. If you had an LNA, probably since it's a small signal circuit, your substrate is not going to be wiggling around too much. Okay, so in which case you can connect it to its own ground and then just have two connections, maybe ground and substrate connection, guard ring connection. Okay. Other general layout practices. So do a general floor plan first, okay. So that much is that is very important. So the minute you finish designing your circuit, before you start your detailed layout, do a floor plan. Already have in your mind where you want to place certain things, especially start off with the largest things. Let's say if you have an inductor, place it in a certain way. Let's say next thing is where would you place your transistors, where would you place your resistors, capacitors and so on. So you start off by placing them before you start doing the detailed routing, okay. Then plan, when you do the floor plan, you have to plan for a certain signal flow. So let's say if you have an op amp, so you need to find out in the overall layout where your signal is coming in and where your signal is going out. So you need to maintain that signal flow. You can't lay out your op amp such that if your input is coming in from the left and output is going to the right, okay, you can't lay out your op amp the other way around, obviously. Then you'll be routing out like this and then routing out like that. You don't want to do that, okay. So you want to maintain that signal flow. Similarly inside the op amp, okay, so let's say it's a folded cascode, right? You have the input pair, you have the cascode, so you probably want to maintain the input pair somewhere close to the left. It doesn't have to be all the way to the left, but you don't want to place it all the way to the right, because then you'll have input output crossovers and that's usually very bad, okay. So you probably want to maintain it somewhere to the close, and let's say the output cascode transistors, you want them to be as far to the right as possible. Next thing you might want to do is plan your metal weights for your current density and your RC parasitics. For example, you take your VDD lines, you don't care about capacitance, you want to make them as wide as possible. Find out how much total current your circuit is taking, peak current, okay. So plan and give some margin and then you put it in there, okay. And you probably want to stack up multiple metals. If you are connecting, let's say, one inverter to the other, you may just decide to do a smaller, thinner piece of metal. Okay, so those are all things you can plan for. Obviously, VDD ground directions. Okay, where is it going? Is it going to come from the top or the bottom? Sometimes you can flip it. Okay, normal convention is VDD at the top, ground at the bottom, but in the layout it really doesn't matter. Okay, so let's say you have two circuits and they share the same VDD and ground. So let's say you have VDD, you have ground. Okay, so you can do something like this. So you can just flip over. So let's say you have a differential circuit. Okay, you can flip over and share the same ground. Okay, and put the two VDDs on either side. Okay, that's something very simple you can do. if you have, let's say, differential circuits or symmetric circuits, the from a top view symmetry point of view, the best thing you can do is lay out one half and mirror it over. Okay, that will give you absolute symmetry as far as layout is concerned. Okay, you don't have to rely on anything else. However, this may not always be possible. Okay, and it may not always be optimum for a given process. So what happens is, you can think about symmetry at the top level and symmetry at the matching at the lower level. Okay, there may be cases, let's say if you take a folded cascode again, you might have a case where you want to, let's say if you take all the P mirrors, right, you want to place them all close to each other and you want to interdigitate and so on. That basically completely kills your top level symmetry. Okay, or you can just choose to forget about symmetry for the time being, just lay out one half and just flip it over. Okay, normally what happens is, for longer length processes like 1 micron, 0.75 micron and so on, it made sense to interdigitate, it made sense to do, lay out transistors as a unit at the lower level. However, as we go into submicron processes, it's becoming more common to actually lay out one half and mirror it over, that is, look for top level symmetry. Okay, one of the main reasons is obviously dimensions are shrinking to some extent, and you have mismatches at the bottom level and you have mismatches at the top level. Okay, it so turns out you're more worried about mismatches at the higher level. Okay. Okay, so one last thing, I think I skipped it. Yes. Metal routings. Okay. So you have a choice on which metal you want to choose. Okay. So you have, let's say if you take any typical process nowadays, they have 5 or 6 metal layers. Okay, so you always have a choice. And normally the way you would choose is, so let's take the lowest metal layers. Okay, because they have a lot of parasitic capacitance to ground, you don't want to route signal lines on M1 or M2. Okay, you probably want to do, for example, substrate contacts, they all contact, you have to use M1. So at the lower level, as long as you don't have to route a long way, you can use them for VDD and ground. But definitely if you have control lines, power on, power off, or like gain control, those kind of things, you can choose to do M1, M2, and M1 and M2 also to some extent. Okay, M3, M4, they are sufficiently high above the substrate that you can use them for signal routing. And typically, let's say if you have 5 or 6 metal layers, you'd want to restrict yourself to M4. That will give you the most optimum performance. And if you have to cross over some other M4, if you have clashes, then you go down to M3 and then come back up again. Okay, so that is what you would use, and primarily M4. And normally M1 to M4 will be thin metals. M5, M6 and higher metals should usually be thicker metals. Now you may think that, let's say if you take, let's say M5 and M6 are thick metals, right? You may wonder why you don't route the signal on M5 itself. Okay, because it's definitely higher up from the substrate, so it should be lower capacitance. But it so happens so first of all, because they are thicker, your minimum width is no longer the same. So let's say if this minimum width was, let's say 0.2 microns, this minimum width may be 1 micron, something like that. Okay, so if you really want to route short distances, this doesn't make sense to go to a wider metal. Even though it's higher, because it's wider, you'll have more parasitic cap. Okay, the second thing is, nowadays these metals, especially if you go to an RF process, they are so thick that you actually have a lot of fringing cap. Okay, so that becomes more significant than your substrate cap. Okay, so normally you would just go ahead and prefer to do it on M4 instead of going to M5 at all, and that turns out to be the most optimum, even if you are routing long distances. Okay. Okay, then you may choose to use the thick metals to route VDDs and grounds at the top level. For example, once you start combining multiple circuits, your VDD and ground lines start carrying a lot of current, and definitely thicker lines M5, M6 are going to have lower resistance and larger current densities. They can handle larger current densities. So you probably want to go like this. Okay, and obviously this includes a lot of things. For example, it's not just VDD and ground, all high current. Okay, so I think we are done. I don't think we have anything else to cover. I think we have covered most of the things which I wanted to cover. I think as far as the layout is concerned, we didn't get to do a sample layout, but I think that's okay. Okay, we have talked about all the basic practices. If you really want to do a sample layout, you can pick up from where we have left off. I think that's okay. Okay, so yeah, I think we'll stop here, and then I think we are meeting next on Sunday. Okay, so make sure everybody try to attend the 2 weekend classes. Don't bunk it just because it's on the weekend. Okay, the main reason is we are trying to